Hey everybody, welcome back. These are the solutions for the problems from quiz 4. In particular, this video will be about problem 1. So in problem 1, we're given a rational function of s and asked to find a partial fraction decomposition form for it. So as I've mentioned several times, you have almost no chance of being able to find the partial fraction decomposition if you don't know the correct form of the partial fraction decomposition. So this problem isn't asking you to actually compute the entire decomposition, right? You don't need to find the A's, B's, C's, and D's, or maybe even E's. All you need to do here, right, is figure out what form it should be. So the first thing that we notice is that the rational function we've been given has a kind of a strange looking denominator. It's not the product of some linear quadratic factors, at least doesn't look like it. It's actually a quartic, right? A fourth degree polynomial. But we might quickly see here, oh, look, they use an s squared you could factor out of this bottom. So we could actually rewrite this bottom piece as s squared times s squared plus 5. All right, now these pieces, actually, I feel pretty good about them because first, this s squared, well, that's actually, it's not I mean, it is a quadratic, but we don't want to think of it as a quadratic. We actually want to think about this, right, as s times s, or even as s minus 0 times s minus 0. All right, so you can see that this is a repeated linear factor, right? You have the same linear factor occurring twice. And so the rule is whenever you have a repeated linear factor, and it occurs, well, whatever this exponent is, times, then you're going to need to have a summand for each time it occurs. So since it occurs twice, there needs to be two summands corresponding to the s. All right, well, let's take a look and see what we have. So this first one, oh goodness, oh no, what happened? Well, it looks like here they just took the denominator and broke it up across a sum. Oh gosh, no. All right, let's try B. Okay, now B has the linear factor s and then a second copy of it. And that's good, right? Because that's actually the rule you need. If you had s to the n, you're going to need n terms. You'll need an s squared, an s cubed, and so forth, all the way up to s to the n. So this works. All right, let's check C. Well, actually, C has the same thing going on. You have an s and an s squared. Fantastic. Let's see, D. Well, D has an s and an s squared, but oh goodness, they go s cubed and s to the fourth. They must have thought, yeah, that there's like 4 repeated s's, and so they did 4 of these. Yeah, that's almost just as bad as A, because look, even then they just broke it up and had another 5s squared. Yeah, this isn't even close. Okay, now what else do we have? Well, we have an s squared plus 5. Now, we don't actually factor that anymore because this is what we call an irreducible quadratic, right? We cannot factor this over the reals, all right? Any roots of this would be imaginary or complex numbers. So we're only going to be able to leave it in this form. Fine, but B and C both have that, so that makes us feel pretty good. Actually, what's the difference between B and C? Well, let's see. On top, we have A over S, and well, there's A over the S. And then we have B over S squared, and B over S squared. So they're actually the same in the first two summands. So the only difference is in the numerator on the S squared plus 5 term. And this is where we have to understand how the form works. Right? When we have an irreducible quadratic, we need in the numerator not just to have a constant, but to have a true linear function, right? At least in our general form. So in the end, C is the only form which is going to meet all the criterion we need for our partial fraction decomposition.